and set up a whiteboard. So let me know when you get my whiteboard.
I got it.
Got it?
Yeah, got it.
Okay, so what I'm going to do, we're going to start with the metric, the cur metric. This will take me about 20 minutes to write the whole thing down.
Oh no.
It's
Wait, did I?
it's
Okay, wait.
there. Easy to fix.
Well, I was trying to zoom in.
It's perfectly fine.
Oh, I did it. I did it. We're good. Yeah.
This is all natural units too. I'm just taking it from that thing I gave you on uh, from Carol. So next week we're going to meet on both Thursday next week and the Thursday after that next week, and then I think we'll be able to get exactly where what I want to get done. Now, are you both going to be around? Because I'm going to be meeting with Jacob to go over some stuff on gravitational waves. Are you going to be around as well, Jake?
Um,
Or don't you know?
I'm not sure yet. Like
Okay.
after the semester,
Yeah.
I'm not sure yet.
Okay.
I would find
I'm going to record them anyway, so you can certainly look at the material.
sweet. Thank you.
Yep. Okay. So where the row, um, well, okay, I won't give you what the row squared is and the delta squared is, just so we can start going, um, developing this further. I'll write down the rows and the deltas when we need them. So I had this here, and what we want to do is we found we looked at where the infinite redshifts were. So the infinite redshifts. Okay, where did they occur?
At
What was the condition? It had to do with this term right here. We wanted that to be 0. So remember what we did is we said we could say if we have a proper time, we'd have this g tau squared would equal this minus g tau squared. Would be this minus would be this GTT. And then we said in order for this to basically have these infinite redshifts, we need this coefficient to be 0 here so that these GTs would be infinite. And that this would be the infinite redshift. So if the GTTs are equal to 0, that means that this rho squared here is equal to this top. Is equal to that. And these rho squareds are given by, now I'll write these down, are given by this guy here. Right, this was our rho squared. And we want this to equal these 2G MR. And we saw the quadratic equation when we got those, and we saw that there were two of those. Does that make sense?
Yeah.
That's all good? And then we also found out, so this is one thing we did. Then the second thing we did is we wanted to find out where the dr for light, the dr dt equals 0 for light. Okay, that's going to be too much for me to actually write because that was quite involved. But if you remember what that ended up equaling, we ended up with this dr dt equaling delta times a whole bunch of stuff. So there's a massive equation there. And the way that you'd make this to be 0 is that we then want this delta to be 0. And our delta in this case here, our delta is this r squared minus 2gmr plus a squared. Okay. So, and that gave rise to basically two event horizons here. And we said if we plotted these event horizons here, they kind of nested in terms of each other like this. They did not do that at all. We said if we had one of them here, so this would have been one of the event horizons. What happened is that if you look at one of these infinite redshifts, the infinite redshifts look like this. Okay, so this was the infinite redshift. And this was the event horizon. So they don't coincide. And then if you go in the interior, you get another one here like this. You get two other ones like that. And the region we're going to be interested in right now is this region right in here. And so this region right here is called the ergosphere. And then I should mention that there's one other thing we did. We looked at the singularity. And the singularity is going to occur basically where your curvature is infinite. And the curvature becomes infinite when this rho equals 0. And we solved for this, and that actually gave rise to a ring singularity. Okay, so that's what we did last time. Does that all make sense?
Yes.
Okay.
Yeah.
And if you're to have any of the other black holes, this is actually the analysis you would do with all these. So you'd find out the infinite redshift, you'd find out basically your event horizons, any singularity. It's kind of the standard thing you do with any of your black hole calculations. Okay, so what we're going to do now is I want to look at inside this ergosphere here because it actually has a very bizarre property, and it's going to be called frame dragging, and I want to set this up. So actually, let's start doing this. So let's look. So this will be new stuff here, and let's go over here. So let's look at inside the ergosphere. Okay, since I'm teaching a course in Koine Greek, let me just put in some Koine Greek thing here. Okay, if you're wondering why it's called ergosphere, there is a Greek word called ergon. Okay, and ergon is the Greek word for work. If you remember, what are the CGS units for work?
Newton times distance.
Okay, that would be the
Um,
MKS unit, and
uh,
a Newton time distance is a joule. But what is the CGS unit for it? Physics and astronomy majors.
Is it just an EV?
CGS. Okay, that
No.
again, if I had my white fluffy cat here, I'd be petting my white fluffy cat, and I'd be pressing some button, and the walls would start coming in on your room, Jacob. Okay. Okay, the EVs are not going to be CGS units. That's what when you're using quantum mechanics. You're going to measure energy in terms of EV. So, okay, so if you have your MKS units, okay, if you'd have work, you're right, it's force times distance. So the units, again, I'll use brackets for units. This would be a Newton times a meter, right? And this is a joule. Okay. And if you're in CGS, that's a sad CGS. Okay, what does CGS stand for?
Centimeters, grams, seconds,
That's right. What happens? Okay, so what do you measure then a Newton in terms of?
kilograms, or well, grams and centimeters per second squared.
Okay, which is a dyne.
Oh,
And then I should put my joules in brackets here. And then your distance is measured in terms of
centimeters.
centimeters. And a dyne centimeter is by definition one. There's a reason why I gave you the Greek. One erg. Okay. So the erg comes from this part here, the Greek. Okay. And the ergosphere here, the reason it's called the ergosphere is that part's actually going to do work on our object. Okay. That's why it's called the ergosphere. Okay. It's just not that somebody just randomly came up with something. There's a reason for it. Okay, so maybe it was good to do the units after all. So that was good. Okay, so going back to this. So we want to look inside the ergosphere, and let's look at the angular velocity. The angular, let's say, yeah, let's say velocity. Okay, of light. And since we want to simplify this a little bit, we're going to say when theta equals 90 degrees. So you tell me how to do that.
we'll set ds squared equal to 0,
Okay, so you're going to say ds squared equals 0.
and then d theta is 0.
Okay, so instead of this piece here, I'm going to write this in, I'm going to call this whole piece here GTT. So we're going to have GTT dt squared. Okay. Then what is this piece here going to become? This whole piece here, I'm going to call this G phi t. And again, what this is going to become in this case here, this will become really our minus 2G. Ooh, that's really sad. Two GM R. I dropped my A. 2GM A R. The sign goes to 1 over rho squared. So I'll say then this is plus G phi t dt d phi plus d phi dt. A little bracket there. Okay, plus, what will this piece become?
GRR
Okay,
DR.
for angular velocities,
Oh,
what is our
yes,
R going to be?
fixed.
It's going to be fixed, so that term is going to become
0.
0. So I'll have 0 there. Plus, what will this piece become?
0 because theta is fixed.
Theta is fixed, so that'll become another 0 plus. Okay, I'm going to call all this piece here. Actually, I'm going to call all this piece here. Okay, I'm going to call that G phi phi. And again, my sine of theta is going to be 1. So this will become R squared plus A squared minus A squared delta. And again, my sign there is 1 all over rho squared. So this will become plus G phi phi d phi squared. Does that make sense?
Yes.
Yes.
Okay. So I'm going to divide everything through by the dt squared. And if I do that, that'll give me 0 equals GTT plus, and again, these terms here are really the same. So this will become 2G phi t times what? If I divided everything through by the dt squared.
Times 2 d phi dt. Or no, you
Yep,
already
yeah,
2
d phi
the
dt.
2.
Plus, what's the last term?
G phi phi d phi the dt squared.
Yep, d phi dt quantity squared. Okay, now if I want to solve we want the angular velocity, so we want d phi dt. So what is that going to equal?
Quadratic formula.
I agree. So tell me what it
Yeah.
is.
2 g phi t.
Minus 2
Oh,
g phi dt, g phi g phi t, plus or minus.
square root of 2 g phi t squared
Okay, so I'll write this as 4 g phi t squared.
-4 GTT G55.
Yep, let me let in Junior.
Junior.
Oh, we just keep on going. But I just let him in. Because this is, oh, there he is. Hey, Junior.
Hello.
Junior.
Yeah, I'm a little late.
We started off with basically a period of silence for your absence.
Oh,
And then Jake and Jacob basically then gave a little speech about you. Hey,
oh,
Zephyr,
oh, oh.
there was
Hey.
a little poem that they wrote. And then
Oh,
we had another moment of silence and we had a little song. And then we
yeah.
started class.
Oh.
So this is going to be our G5, G55, GTT. And this is all divided by what?
2G55.
2G55. So, Junior, what we're doing is we're looking at the curved black hole.
Okay.
We went in, we're basically we went inside the first event horizon here. I mean, I'm sorry, the first infinite redshift here, and here's our first event horizon, and we're in between this region here, and this region in between here is called the ergosphere. So we're in the ergosphere, and what
Okay.
we're looking at is we're looking at the angular velocity of light in the ergosphere. And so we went back up to our metric here. This is our Kerr metric. Since we're looking at light, we set our ds screwed to 0. We're going to take theta to be 90 degrees because it's just easier that way. And our r is fixed. And so when you do that, the metric reduces to this big mess here.
Yeah.
And instead of writing this whole mess again, we've just been calling these like GTT, G phi T, and stuff.
Okay.
So we have this. Okay, we can clean this up a little bit more. I can write this as G phi dt equals. So this piece here becomes what? The twos cancel. This becomes minus G phi t over G phi phi plus or minus. And then I can take the G phi phi inside the square root. And that means I have to square each of the terms. And I can write this whole thing then as the square root of G phi G dt. I mean G phi t over G phi phi quantity squared minus GTT over G phi phi. Like that. Okay, does that make sense?
Yes.
Yes.
Okay.
Yes.
Now, this is kind of a big mess that you could work out this anywhere inside the ergosphere. Where people work this out, because it actually turns out to be simple, is let's evaluate this. So evaluate this. At basically the infinite redshifts. In other words, let's say if I've just popped my head inside this ergosphere here. So I'm right here at this first surface here. Now, what did we say happens at these infinite redshifts? What was the condition for that?
Rho equals 0.
No, that was the singularity.
Oh,
That the GTT is 0.
Yeah, the GTT is 0. And this is nice because that kills this term here. Okay? And so what do you get here? You get the square root of the square. And so you're left with this G phi dt is equal to G phi t over G phi t over G phi phi. That's a really sad phi here. That's a phi. Plus or minus G phi t over G phi phi. Okay, what are the two solutions you get then for this?
Minus 2G phi t over G phi phi or 0.
Exactly. Or 0. So before we look at the 0 one, and that's going to be the really interesting. Well, they're both actually very interesting. Um, let's actually figure out what these are here. So the easiest way to let's actually calculate this guy here. So we actually before you put in numbers here or values, let's evaluate what these are at this point here. So I'm going to go to another page. So if I go here. Hey, everyone have my new web page? I mean, my new whiteboard?
Oh,
Let me know when you have it.
you got it.
Got it? Okay. So let's evaluate. The G phi t and G phi phi at GTT equaling 0. So let's go through and do this again. So recall, your GTT equals 0 when your rho squared equals 2GMR. What is our rho squared? Our rho squared is my buddy here. It's this r squared plus a squared cosine squared of theta equals 2, ooh, not that at all. Yeah. There. Now, but what do we know about theta? What do we know about this term here?
The term 0.
Yeah, our theta, we're taking theta to be 90 degrees. Why? Because basically it's going to make life easy for us. And so this gives us r squared equals 2GMR. So this really means that our r is going to be 2GM. So we're going to evaluate these terms at this. So what do we get for this? So we have our G phi t is, I'll put down the whole messy thing here. So we have that mess. And then our G phi phi is even worse. It's this sine squared of theta over rho squared times a really painful thing. R squared plus a squared minus a squared delta sine squared theta. And this delta here is, again, remember that this delta here is r squared minus 2 G M R plus A squared. Okay. So let's try to calculate what they're going to be at when theta is 90 degrees, and then we're at the first infinite redshift. So I'm going to take this guy here. I'm going to pop this into here and here. So what does this give me? This gives me 4 G squared M squared. If I put this in here, this also gives me 4 G squared M squared plus A squared.
Wait, how come 4? Because R squared is equal to 2GMR. So if you put R squared there, it shouldn't be just 2GMR again?
When you square 2, you get a 4.
Oh, okay.
When you put it in here, you pick up the 2 from this guy here.
Yeah, okay.
So they cancel, and this tells me that at that point, our delta just becomes A squared. And then what is our angle is 90 degrees, so this goes to 1. So this whole thing here becomes what? This G phi becomes 1 over rho squared times R, and I'm going to, you should yell at me too. This guy comes in squared. Okay, I forgot that squared. Sorry about that. So if we square that guy, that's going to give us what? Well, actually, let's put in our value for this as well. So this will give us the R squared is going to be 4 G squared M squared plus A squared minus, and then this delta here is A squared, so there's another A squared in front, so this is A to the 4th. That makes sense? So this gives us 1 over rho squared. So if I square this guy out, I'm going to get 16 G to the 4th M to the 4th. Plus I'm going to get twice the cross term. So that'll give me 8 G squared M squared A squared. Then twice this guy here, or that guy squared, A to the 4th. And then I have the minus A to the 4th. So they cancel here. So that tells me that I'm finally left with G phi is, and I can pull out I'll just leave it like this. 16 G to the 4th M to the 4th plus 8 G squared M squared A squared all over rho squared. And that looks way too sloppy here because I'm not going to be able to read it in just a second. So I'm going to rewrite this so it's coherent. M squared A squared. Does that make sense?
Yes.
Okay, now go ahead.
Can you put in, since we have rho squared, can't you put in like 4 G squared M squared in for rho?
We can, but I'm going to be lazy here because we're taking the ratio, and those rho squareds are going to cancel.
I see.
Okay, but what you said is completely correct. So now I'm going to deal with this guy here. So this is my G phi t is going to equal then our minus. And then if I take this R and put it in for this guy here, what do I end up with? I end up with 4 G squared M squared A all over this rho squared. Because my sine is equal to 1. Because it's at 90 degrees. Does that make sense?
Yes.
Yes.
Okay, finally we can put it all together. Okay, so we get our G phi dt. Remember how we said that one of the roots was this? Okay, so if I put in this guy here, if I put in, where the hell did it go? Oh, up here. Okay, so if I put that guy up here, that's our minus 4 g squared m squared a over rho squared. And divided by my buddy here. Oh, that's sad. This will simplify greatly. It may not be obvious, but it's going to simplify a lot. Ooh, that's sad. Hmm. Okay, those stupid 1 over rolled squares go out. And then what do I'm left with the top here? At the top, I'm left with a positive 8. G squared m squared a. And then I have this bottom here. I can divide both sides by 8 g squared m squared. And if I'm left with that, then I have a over. So if I divide this term here by 8 g squared m squared, I'm left with 2 g squared m squared. And when I do this one here, everything cancels with the a squared here. Now I'm left with this. Now remember, this is light. So we have this one here. So we worked out that one here. We had this solution here. And then our other solution. We didn't have to do any work because basically it gave us, it was this. So interpret these results. Okay, what does this A represent again? A was the what? Angular momentum per
per unit
Unit mass.
unit mass. So what's happening here? So what do you know about the angular velocity here of the light? It has to go in the same direction as which the black hole is rotating. So if here's our black hole like this, I can imagine this thing is rotating about this axis here. This is A. If I'm right here, that light has to go in that same direction. So in this case here, light would be going into the board like that. Now light would have to be traveling in that same direction that the light is, which the black hole is rotating. So now interpret this solution for me. It's a wild solution.
Well, the light doesn't go anywhere.
So which way is it trying to go?
Alone.
In?
It's
Okay.
trying to come out. It's basically, instead of, if I do a top view here. So here's my black hole. Okay. What's going to happen is that in one case, so let's say my black hole is rotating this way. I'm doing a top view, so the z-axis is coming out of the board. In one case here, the light is going this way. That's my d phi dt. This one, the light's trying to go this way here, but it can't. Instead, what happens is that the d phi dt equals 0. So light's trying to go this way, but it can't. What's happening here, this is an example of what's called frame dragging. and the space itself is physically being moved. So the light is going this way, but the actual space itself is actually being rotated with the black hole. That's what's happening with this. And so the light tries to go forward, but the whole space is pulled back. Okay, so this is frame dragging. This is brand new physics. And so there is something called the gravity. I don't even think you were born at that point. There's something called the gravity B probe. And what it was a very, very precise, extremely precise gyroscope. And the whole idea was to basically take it and put it outside actually just outside the Earth. The Earth would be rotating, and it'd be a weak Kerr black hole solution. But if you had a sensitive enough gyroscope, it would actually take the space. The Earth rotating would actually take the space outside of it and actually rotate it with it, and that would actually cause a precession in the gyroscope. And they actually tried to measure the frame dragging with the Earth. The problem is that there was a problem with the probe, and so the results were inconclusive and whatnot. But I think they just need. Actually, one of my former students, he suggested what they should do is do that same experiment, but send it actually to Jupiter, because Jupiter, rotates at some idiotic rate. And then you'd have a much larger effect there. And I thought that was actually a brilliant suggestion on his part. I don't know why that didn't occur to people. As soon as he said it, it's like, oh, his name was Phil. It's like, Phil, brilliant. That was an excellent idea. So, but that's what we're getting here. This is brand new physics here. Does that make sense?
Yes.
Okay, that's just quite cool for this. Okay, so the next part we want to do, I am worried about getting through the stuff with the cosmology, and I love cosmology. Cosmology is just one of my favorite subjects to deal with. So I want to make certain we do that. I'm going to take part of the Penrose process and I'm going to write it up into an assignment so you can kind of see what's going on with it. The whole idea is there's that one. Do I have it with me? Maybe I took it to school, or it might be elsewhere. Um, um, John Wheeler has a way of describing it, and he describes it. It's basically going to be a way of. Let me try to draw a top picture here. Okay, so you're in the ergosphere here. You're basically you're gonna hop inside the ergosphere with like a rock. And you're going to take your rock, and if you set it up in such a way, you can send your rock this way here. And from conservation of momentum, you kind of get kicked out here. But what's going to happen is that you come in with positive energy. So your energy here is positive. You can set this up so that when you're throwing this in here, the object you're sending in here actually ends up with negative energy. But you know that this energy here and this energy here, if you add them together, have to equal this energy here. So the energy here is actually greater than your initial energy. Like that. That's the whole idea behind the Penrose process. And what happens is you're not creating energy. What it ends up doing is you're extracting rotational energy from the black hole. So that's why this is getting more energy here. And I think it was John Wheeler has a way of describing it in terms of a bank. He says, suppose you and your buddy basically, you have a bank account and your bank account is positive. So you both have positive money. And what you're going to do is you're going to give all your money to your friend. And then you're going to go to the bank because you have no money. And you're going to get a whole bunch of money from the bank. Let's say $1 million from the bank. And then you're going to give that $1 million to your friend that already has money. So what's going to happen is your friend is going to have, the money you gave him plus $1 million. And you're going to then declare bankruptcy. So you're left with zero. But your friend is left with $1 million plus whatever he started with, and the bank is left with basically the deficit. He says this is kind of what's going on with this process. I thought that was kind of funny. So, but I'll start you off with this. So when you do the Penrose process, it comes down to looking at the the killing vectors. So if we go back here, there's a lot of stuff here. I apologize for this remarkably messy whiteboard. Um, what would be the killing vectors connected here? Again, remember the killing vectors, you look at all the G's, you look at all the G mu nus. You look for all of them, and there's going to be, if there's a killing vector, this G mu nu will not depend, all the G mu nus will not depend on one of the variables. So are there any killing vectors in this problem here? And the way I'm setting it up, the answer is obviously yes. But what would it be? I give you a hint. It's a lot like with the Schwarzschild black hole.
It's going to be 1,0,0,0 and 0,0,0,1.
Exactly. This right, if you look at all these coefficients here, all of them, none of them depend on t. So we have a symmetry in t, and also none of them depend upon phi. So we're going to basically have a k mu, which will be our 1, 0, 0, 0. And then you're going to have another one here I'll call eta. And the eta is going to be basically your 0, 0, 0, 1. And the difference is when we work these out, these are going to become a lot more complicated expressions. And they're going to become a more complicated expression because of basically this guy right here. Because this guy both is a mixed term here. Depends on both defined dt. And so what I'll try to do is come up with a little tiny exercise to basically do that. But what I like to do is, actually I can stop sharing this now. Okay. What I like to do on Monday is I like to start cosmology. And because I like it, I like cosmology a lot, an awful lot. And so we're going to start off with the model that we're going to use, which is on large enough length scales, the correct model to be working with. So I want to set that up, and it's really pretty cute. And so what I want to do is set up all the stuff with cosmology. We could have a whole course in this, and in fact, Jacob, you actually had a course in it, galactic dynamics and cosmology. So you'll see it again.
Yeah.
Okay. Questions? Okay, so I will let you guys go. I will okay, my wife and I live in the country. You can see the woods back there. The internet here is remarkably bad. It when I upload the lectures at school, it usually takes about 10 seconds. Here it takes on the order of an hour. It's remarkably slow. So I'll upload as fast as I can the lectures. In principle, the whiteboards are saved. If somebody wants to take has anyone taken a snapshot of the whiteboards? Okay. If you want to take snapshots of them, just in case I can't get hold of them.
No.
Can somebody take a white snapshot of that? Assuming, let me try to make it bigger.
Yeah, I have them.
I think it's all on there now. Did you have a did you take a snapshot?
Yes, I did.
Yeah.
Okay, let me go to the next one. And everyone have that one?
Yep.
Okay,
Yes.
good. Okay. So, with that said, we'll call it quits. So we'll meet next Thursday and the Thursday after that. And then as far as a third test goes, our options would be not to have a third test, and I'm happy with that. Or if we had another third test, I would suggest it to be a take-home third test. Now, it's getting toward the end of the semester. Everyone's busy. There'd obviously also be a final. So I don't know if you want to have a take-home third test and then a final kind of back-to-back, or you're just happy having the two tests. I don't, there's four of us. We can do whatever the hell we want. I mean,
I'm
Yeah,
fine
I have no
either.
preference.
you have no
Yeah.
preference?
I'm fine with whatever.
Okay. Hey, Bill. And Zephyr is there too. Okay. They're keeping
Yeah.
you company. See? They don't want you to, hey, Zephyr, they don't want you to be scared by all the general relativity equations. Getting stuck in a rotating black hole, hitting that ring singularity, meeting yourself in the past, it'd be awful. They're keeping, they're watching, they're looking out for you.
So Dr. Lax, I do have a question. So
Sure.
yesterday, I did the test and I just wanted to like check real quick about like my derivation of the Riemann curvature tensor. So,
Okay.
but you weren't there. You disappeared.
Yeah, I didn't know. I waited a while, then you weren't there, and then I remembered we had talked about something going on and stuff like that.
Yeah.
So I just figured you had some complication. I'd see you today. I was planning on being in today, but last night was not a good night for me. So I
Oh,
thought it was best if I stayed home today.
okay.
Okay.
So can we go over it on Monday, you
We
think?
can do it right now if you want.
Oh, okay.
Or, or,
Well,
or did
I
you,
don't
or
I
is
don't
this,
I don't
is that
have it
too
with me.
soon?
It's in your mailbox.
Oh,
And
okay. Then maybe Monday might be a better thing.
yeah.
Okay. We can go over it Monday.
Okay.
What question did you have with it?
Uh, just to know whether I was going to, I mean, I did get the results you wanted me to get, but I don't know if what I did was correct.
What
Because
did you do?